Hello. In our last lecture, we had discussed the network edge and the access network, that from the edge machines, PC systems, iPads, phones, how do we access, what kind of link there are, and so on. At the home, we use DSL link. Within the home, we have a Wi-Fi or Ethernet, office Ethernet, which could be 100 Mbps to 1 gigabit. Then so on. As servers, clouds are connected via optical fiber link, another kind of scenario. In this lecture, we will discuss network core. That is, how does the various internet devices, the core network which we discuss, are connected of. So primarily, if you see, the core network consists of these routers in the ISPs or the regional ISPs and so on and so forth. So network code we look at as more of a mess of interconnected routers. Now how do these router works? Primarily when application, let's look at the application here. I have an application here in my laptop sending data. Application, I'm sending a big message, let's say I'm transferring 1 megabyte file. So whole 1 megabyte file doesn't go as a single packet. This 1 megabyte file is broken up into multiple packets. Let's say each packet 1000 bytes. So we'll be sending our 1000 bytes packet each time. And what happens is my laptop will send a packet to next sub router, and then it will send a packet. So application sends multiple packets to the router, and router forwards one packet at a time, one packet to next, next to next, next to next, and so on and so forth. So you can basically see the packet would traverse something like this and go back to the other machine, something of that kind. This is how the packet switching takes place. Now when the packet is transmitted on a given link, which is a Wi-Fi link, if my capacity is 11 Mbps, it will be transmitted at 11 Mbps, or if the packet is, I'm using Ethernet, 100 Mbps, it will transmit it at the 100 Mbps and at that rate. So we transmit each packet, and these links are, we can say, either half duplex, full duplex, or even we can call them simplex as well. A simple example, simplex, would be, let's look at a one-way road. If your road network in a city, in a particular street, traffic is marked as one way, that means people can go or cars can go from one end to the other, but can never ever come back from other end to this side. This is called one-way road, and this is called a simplex traffic. You look at a highway, any typical highway, let's say we have a highway and we have a, let's say, 4-lane highway, and we say these 2 lanes are going in the east to west and these 4 lanes are going west to east. So these 2 highways, my traffic is going in both the directions, east to west, and it also going west to east at the same time. So this is full duplex link because the entire, if you look at my entire road is carrying traffic in both way directions, and in that sense it is called full duplex. It will be half duplex if, for example, you consider a bridge where traffic can go only one at a time in a direction. So let's say I have a bridge, and on bridge only one vehicle can pass in one direction. So this has to be used, but traffic can go in both directions. So let's say first 5 minutes traffic goes east to west, and the next 5 minutes goes west to east. So at a time, link can be used only in one direction, but allow traffic in both directions. That is what is called half duplex link. So similarly in the computer networks, our links are full duplex, half duplex, and simplex. Simplex link will be those where traffic can go only one direction. Let's say if I have a satellite dish, when I receive my cable TV or dish TV, I only receive signals on the dish. I don't send any signal back. So this is a simplex. On a telephone line, if you look at when we talk to other end, Our conversation happens both ways. But when you're talking, either the person A speaks or the person B speaks. So traffic communication traverses on this telephone line in one direction at a time. If A and B are talking, when A speaks, data from A to B goes, and during that time, when A is speaking, B doesn't speak, so there's no data coming from B to A, and vice versa. So the link between the telephone link between A to B is both a possible duplex link, but it is used as a half duplex. But when you look at the Ethernet, I'm sending data, I'm receiving data at the same time, that becomes a full duplex link. Now we've seen that we are sending packet and different links can have different bandwidth. So let's look at in this diagram here. A is connected to the router with a link of 100 Mbps, and let's say B is connected at a smaller link of 2 Mbps, or both, let's say both A and B are connected with a link of 100 Mbps bandwidth. But the outgoing router has a link of 1.5 Mbps. Now in this case, both A and B send traffic at the full rate. Outgoing link is only 1.5, where receiving link is 100 plus 100, 200, and the outgoing link cannot support this, so this has to drop. Now this router which we have here can buffer packet for certain time. It can do buffering for whatever buffer memory is available, but once buffer is full, it's going to drop the packet. So typically what happens in the internet, when sender sends the packet, they come here, and there is the link is choked, the traffic is transmitting, it will keep in the buffer, and if buffer is full, it will simply drop the packet, and when the packet is dropped, they need to be transmitted. And there's the moment the packet is dropped, we basically say there is a packet loss occurs, and the packet gets queued, the buffer is available, we say queuing has occurred. So queuing is packets are queued into the buffer, and the packet loss is when packets get dropped, that is called loss. And in both the cases, if packet has been queued for too long, then the packet will be reach other end, and other guy be one timeout, and you think the packet may close the connection. So some delay in queuing may be fine, but longer delay in queuing may not work. Packet loss happens, it has to transfer it again. So let's try to understand simple scenario, how much the loss could be, and when the packets are dropped, router do have a choice whether to drop the first packet or the last packet or packet in the middle, and there are different queuing strategies that we use in dropping a packet. Let's look at a simple example here. We have a machine A which is sending at the rate of 10 Mbps, machine B sending at the rate of 5 Mbps, and router R1 outgoing link is 3 Mbps. Let's say A sends at the full rate, A is sending packets at the full rate of 10 megabit per second. So assuming each packet is 1 megabits, so that means A keeps sending 10 packets every second, each of 1 megabit, and B keeps sending 5 megabits full rate, that is 5 packets of each. And so a router R1, if we look at router R1, will receive 15 packets of 1 Mbps, 1 megabit every second. It can transmit only 3 packets per second, and that means it has to drop 12 packets per second. Even after whatever queuing buffer is full, it's going to drop 12 seconds. Now assuming that my router is fair to the incoming packet, that means it treats all packet equal with equal weightage, equal priority, does not distinguish between A and B, then when A is sending a data to C and B is sending a data to E, and where A is sending all the 10 packets of 1 megabit each per second and B is sending 5 packets each of 1 megabit second, what is the rate at which C would receive the packet and what rate E would receive the packet? Give a thought, pause the video, think about it, and then come to the answer. Assuming you worked out the answer, let's look at what really happens. Router R1 is receiving 15 packets per second that we discussed. Router R1 is receiving 15 packets per second, but it can transmit only 3. That is going to drop 12 packets, and we say it treats all packets equally. That means it's going to drop 12 packets. Since there is coming full packets, so what R1 will do, it will drop 8 packets of A and it will drop 4 packets of B. That makes it 8 plus 4 is equal to 12, and that means B will be sending 1 packet per second and A would be sending the effectively on this router link 2 packet per second. So that means packet rate at C, what he will receive would be 2 Mbps and packet rate at D would be 1 Mbps. Just to make sure that you understood correctly, let's do next exercise. Consider that router, the host A is still 10 Mbps link, B is 5 Mbps link, router R1 bandwidth is 5 Mbps, is not 3 Mbps. But now router R1 treats both A equally, A and B equally. It's not the per packet basis. It gives the router R1 gives equal weightage to A, equal weightage to B. That basically means this bandwidth, if it's a full load, would be equally shared, and that means 2.5 would be shared by A and 2.5 for the B. Now your question is, at what rate packet would be received at C and D? So what rate C would be receiving and what rate E would be receiving? Pause the video, work out the exercise, and think about it. Now, as you've already said, since our router R1 is treating both A and B equally at the fair rate, that means out of the 5 Mbps, it will give 2.5 Mbps to A, it will give 2.5 Mbps to B, and other packets would be dropped. So C would be receiving at the rate of 2.5 Mbps and E would be receiving at the rate of 2.5 Mbps. Other alternative to the packet switching what we see is what is called circuit switching. That is what we observe in our when you make a voice call in telephone networks. Is typically circuit switching. In circuit switching, what happens does not matter whether we use a circuit or not. It's something like you can look at when you're driving on a road. Now, one particular, let's say, lane is reserved for government vehicles, and if one particular lane is reserved for VIPs, for CMs or PMs or something, and no people can walk on. So the CM may be traveling only once in a day, but other people can't use it, that road is reserved. So if we reserve a particular circuit in the same way, so if let's say a number of links, let's look at in this case, in this diagram, consider I have a router A, router B, router C, and router D, and each router A to B I have 4 links, B to C I have 4 links, C to D I have 4 links, and A to D I have 4 links. And that means, but on one link, only one machine can use. Now let's say I have 4 machines, which is mark them as, let's say, P, Q, R. These are the 3 machines I got. Now P wants to communicate with C. It sets up a link. When it sets up a link, it needs to reserve the circuit. Doesn't matter whether you use it or not. So let's assume P reserve second circuit from this link and fourth circuit from this link. So if you look at P makes a call, such second circuit get reserved between this router A to B, and then between B to C it reserved the fourth link, and then traffic. So now look, the entire circuit between the 2 circuits A to B and B to C are reserved. Doesn't matter whether P is sending 1 packet, 1 byte per second or 1 megabyte per second, depending on capacity. this circuit cannot be used by other machines. Let's say Q to send to some machine sitting here, connect to router D or other places, it cannot. So this circuit switching guarantees P that anytime you want to send, circuit is available, packet would go, there will be no drop that will occur, but it is a very, very inefficient use because when P is not sending to R, this circuit is lying a waste, Q can't even use it, that becomes a waste. So circuit switching gives you guarantees, but at a very high cost of very, very inefficient utilization. And so look at this, when I do circuit switching, we are not sharing the resource because circuit reserved. If we were to use packet switching, that means this circuit would be used only when P is sending, or between B to C, the circuit would be used only when P to R is coming. P to R is coming. When P2 is not sending, then Q can send full bandwidth and Q can send the traffic here as well. So in circuit switching, we share the resources. In packet switching, we share the resources, links. In circuit switching, it's dedicated and we don't share the resources. So we should use circuit switching if a regular continuous traffic to send. You should use preferred packet switching. If we have not 100% time occupation, we send at any point in time randomly. So in general, that is the case. Like when you're doing a browsing, you type a URL, it will probably send 1000 bytes, but after the next 2 minutes, you're watching the image or you're reading the content, you're not sending anything. So you don't want to reserve any circuit. So whole of internet technologies, we basically use packet switching and not circuit switching. So just look at the example to understand how does packet switching works versus circuit switching. Consider there are n users connected. I have n users connected via router, and router, my outgoing link is 1 Mbps. Now, each user is active at the 10% of the time. That means each user sends data only 10% of the time. Other 90% time, it remains idle. And each user, when it sends only 100 kilobytes of data. So look at here, my outgoing link is 1 Mbps. If all the 10 users sending at the same time, it can support because each user is sending only 100 kilobits. So 10 users would make it 1 Mbps. So that means if all the 10 users send at the same time, it will be fully used. And if more than 10 users send at the same time, some packet has to be queued. Now, in this case, what should happen and what should the relation would be? If I were to use packet circuit switching, in this case, if I were to use circuit switching, I need to reserve the circuit for each user. Now, since each user needs 100 kbps, so I'll reserve 100 kbps for user 1, 100 kbps for user 2, and so on and so forth. And I can support 10 users. Others have to wait, they cannot be served. But if I were to do packet switching now, can I support more users? How much I can support, and that's the question. So let's take a question. We are given 20 users. Each user sends 100 kilobytes per second when active. That is when it sends. But user is active 10% time. That means out of 1 hour, which is 60 minutes, user will send only for 6 minutes, and remaining 54 minutes user would not send. But whenever user is sending, it will send at the rate of 100 kilobits per second. Given that, can you compute the probability that how many users can we serve all these 20 users in this link? Given that a user is active 10% time and n is equal to 20, so what is the probability that all 20 users can be served at the same time? To understand this problem, look at it in the following way. Probability of one user sending is 10%. That means user active is 0.1. Now that means the probability of user not sending is 1 minus 0.1, which is 0.9. Now let's say only user 1 is sending. If only user 1 is sending, That means remaining 19 users are not sending. So if you have a case where only one user sends, 19 user doesn't send, this will be probability 0.1 raised to power 1 and 0.9 raised to power 19. That's the probability. So similarly, if you are looking at the case where we look at only k users sends at the same time, exactly k users, no more, no less. We have exactly k users sending. So using binomial theorem, we know out of 20 users, the possibility of any k could be 20 ck. This would be a possibility of picking any k users, and for given k users, probability of sending would be 0.1 raised to power k into 0.9 raised to 20 minus k. Now we are saying probability that we want to make sure that our links are not choked, all user can transmit. That means if no user transmit, we are fine. If only one user transmit, we are fine. Or two user transmit, we are fine. So up to 10 user transmit simultaneously, we are fine. But the moment I have 11th user coming up simultaneously, 11th user has to wait. So what is the probability of 11th user transmitting? We have to discard. Probability of 12th user transmitting simultaneously, we have to discard. So we can do compute the sum of all the probability of sending 0 user, 1 user to 10 user, that is sigma I is equal to 0 to 10, 20 Ci, 0.1 is to power I into 0.9 is to power 20 minus I. When we sum up, the value comes to be 0.99999291. That means in a given case, we know that all 20 users cannot run simultaneously. So probability that if you have 20 users and they'll be successful, probability is very, very high. So if we were to use circuit switching in this diagram, we could support only 10 users. But with using packet switching, and we only 10 a user active 10% time, we can probably support 20 users with the probability of success transmission of 0.999999291. Just to give you further understanding, let's do the next exercise. And the next exercise is, again, router has 1 Mbps link. Assume that, again, users are transmitting 100 kilobytes data when they are active. And case is, let's assume instead of 10% user being active, this time we are saying a user is active 20% time. And there are 30 users. So what is the probability that 30 users could be served in this setup? Case B, take the case of I have each user active 50% time. So each user active 50% time and I have 20 users. So what's the probability that this setup would support me 50 users, each user active 20% time, compute the probability. Work on the same way I've done before. And if you still need more time to understand, there's a beautiful URL given by the Kuros and Ross. So please refer to this link. Is an interactive exercise. There are a lot of examples like this and work out those. They also give you answers. They also give you answers on the website, explain the solution, how does it work. So I would recommend strongly to please visit this website, understand how does circuit switching work, what is the packet switching. And those of you who are not very comfortable or forgotten the binomial distribution, I would recommend watch this video that tells you beautifully how does my binomial distribution works. So all that we basically have to say. So I've done exercise. This should give you good understanding of things. So given this scenario, can we really say, does packet switching always works better? In general, yes. If we have data which we send periodically or in burst mode sometime, but we are not sending data continuously forever. Like we're doing a browser, we type something, we wait for the results. If we're not using a network link continuously at the full speed, then packet switching certainly would work better than circuit switching, mainly because we have no resources, we have resource sharing, multiple users can share the same link, whereas circuit switching, a user get dedicated link, and once a link is allocated to a given user, other user can't use it and become wastage of resource. Second is, in the circuit switching, There is no call setup. We don't reserve a circuit. So implementation becomes much easier and simpler. And that's the reason you look at packet switching, the internet reached a stage much higher, connecting the entire world in about 10-15 years, but telecom took about 100 plus years. Because telecom used circuit switching and internet used packet switching. And it's very easy to set up internet network. Setting up telephone network is too complex and money oriented. So that's the reason. But packet switching has a problem associated with it. If I want guaranteed data, it may not work because other email users will be coming in. You cannot control how many they're just coming in. And if there are too many users, we might have a congestion. And if we have a congestion, packet would be dropped and then we may not build. So if you still want to guarantee circuit-like behavior, that means you have to reserve the circuits. Let's say I want to watch a YouTube video. I don't want any pause in the video what I'm watching. Then I have to make sure that between me and YouTube, a circuit reserved. I have to pay a much higher price, but I may not be watching all the time or wasting the resources. So with that, we basically come to an end of this lecture. But understand, reserving a circuit or giving a circuit-like behavior in a packet switch network is an unsolved problem, and probably it will go to remain like this. And those who still want to get more details on packet switching versus circuit switching, there is a beautiful paper. Please read this paper. It tells you how the packet switching is taking over, and our whole IP network, internet, TCP/IP, is based on completely packet switching, and how it's basically taken a leaps and bounds. Last point is, since we are using packet switching, we have network, we said internet is network of networks. So look at how the connectivity is, and probably a diagram would probably help you better. So let's look at what typically happens. We have the local ISPs, access ISP, which could be your normal city online or your Hathaway or something, which are connected to your regional ISPs. And then at the end, we have a tier 1 top ISP like Airtel or Tata Communications and something of that kind. And there are some companies like Google, they want to give very fast response. So what they make sure is when these ISPs, the two ISPs are connected at peering points, Google have their own servers and every ISP plays so that when you access something, rather than going all the way to tier 1, your content is served locally, and that's how a typical internet structure is. So just to recap, this is a 3-tier architecture. You have a local ISPs, which connect to your home or office. Then you have a regional ISPs, which connect the ISP, and then you have a tier 1 ISPs, which let's say Airtel and Tata Communications, something India. In US, you have a level 3 communications, Verizon Wireless, and something of that kind. So in summary, we studied internet core. We looked at packet switching versus circuit switching. We also looked at if outgoing link has a lower capacity, then it is receiving a traffic at the incoming rate. Packet will be first queued and then dropped, and how the internet work. Next few lectures, we'll look at when packets get delayed, because when you're transmitting, it takes time. Like when I travel on a road, I take some time to travel, how much people I can carry. So we look at when packet goes from A to B, what kind of time it takes, that is what is the delay involved, what are the 4 components, and we'll look at that in the next lectures.